So we're going to be starting 610 today in our new Unit 6B notebook. So if you haven't picked one up already, make sure you grab one. They are in the bin marked Accelerated Math 3, which you already know, but just in case. And we're going to start on page 1 with the warm-up. We're trying to decide whether there's an inverse set as a function, and if it is there, whether it's even, odd, or neither. An even function we know is symmetric with the y-axis, while an odd function is symmetric with respect to the origin. In this particular sense, symmetric, it's rotational symmetry. Rotational. And this one is reflection. Reflect around the y-axis, rotate around the origin. So make a decision. Go ahead and pause your screens and make a decision about what you think about these functions. So number 1 is odd, number 2 is even, number 3 is neither, and number 4 is odd. And 4 is probably the trickiest one because it seems awkward without the rest of the graph because it's, only starts and stops. But if you think about what this is doing right here, this must be doing similar things. This is also odd. If you need to spin your book or whatever, I like to use patty paper to check these out. This understanding is even or odd. And I didn't actually do the rest of this part. I did not read this, whether it was inverse was a function. This one is no. This one is no. This one is yes. And this one is yes. The reason this one is no is because there's something called the horizontal line test right there. And it goes through 3 points, so that means that the vertical line test would also fail after I invert it. Sketch line y equals x for each graph. Remember, the inverse is the reflection across that line. And so this one is no, this one is no, these last two are yes for the first instruction. Oops, sorry, I didn't mean to do that. So I do expect these to be done next time, but I also expect you to be able to do it. So using what you know about the unit circle to draw this graph, this is the parent function, centered at 0, 0, because the sign of 0 is 0, the sign at pi halves, and pi, this is pi fourths right here. So it's counting by pi fourths, or 45 degrees. And at pi fourths, it's 0.707. And at pi halves, it's 1. And pi at 0. And then also at, so pi fourths, 2 pi fourths, 3 pi fourths, it's also 0.707, or radical 2 over 2. So that's the idea. I'm going to give you that first part, and then of course it goes down here. And so you need to do the other side in this sketch. Try to be careful. You certainly can use a calculator. You can use Desmos to help you figure that out, and you're going to do this side. And then for cosine, at 0 the cosine is 1, and at pi halves the cosine is 0, and at pi the cosine is -1, and at pi fourths, 0.707, at 3 pi fourths cosine is negative, at 5 pi fourths cosine is positive, at pi halves it's 0, and at 7 pi fourths and 1. So again, and then you'll need to do this side. So this is the cosine. And this understanding, the ability to sketch that, knowing that it's going to turn around here, it never goes bigger than 1, is important. So I want you to finish the cosine on the other quadrant as well. All right, so let's get started. And I apologize for those words being cut off and blocked. Let's see, scroll this up. So in this task, we're going to go back to the amusement park with Carlos. And we already know lots of things about our Ferris wheel. It has a radius of 25 feet. Center is 30 feet above the ground, and the Ferris wheel makes one complete rotation clockwise every 20 seconds. Nothing new, all the same facts. The amusement park Ferris wheel is located next to a high-rise office complex at sunset. So when the sun is directly across the horizon right there at sunset, the gondola with gondola meaning the thing you're riding in the Ferris wheel, casts a shadow on the exterior wall of the high-rise building. As the Ferris wheel turns, you can watch the shadow of the rider rise and fall along the surface of the building. In fact, you know this equation. The sunset shadow, meaning that the sun is casting a shadow on the building. The sunset shadow, that's terrible. The sunset shadow is our basic sine wave, already know. So this one is the same thing as the distance above the ground, because the gondola on the building is going to go up and down and back up again, and it's not going to do this. It's going to just go up and down and back up again like that. That's what the shadow is going to be doing. But since that's a vertical movement, that is sine. So let's see what we remember. This is the same thing that we've done for a while. So this will be sunset shadow. We're going to use S of t equals the distance moved off the ground, 30, plus the radius times the sine of what? So it was, our other fact was 20 seconds to go 360 degrees, so 360 divided by 20 equals 18. So we've got 18t in here, and that's our sunset shadow. So this is the equation we've been using for a long, long time. Now this is the tricky part. At noon, when the sun is directly overhead, the shadow on the ground. So we talked about this in a video while I was gone, with the shadow on the ground going like this, or the horizontal movement, and our shadow starting over here. So this one is which one? So this is cosine, because we're talking about horizontal movement. And the shadow's on the ground, so it hasn't been moved up at all. It doesn't matter how high above this I am. My Ferris wheel is up here doing its circles. That's not going to affect what's happening. So it starts at 25. This is negative 25, and this is 0. So that's what our shadow is doing. So this, we have the 25, the radius, cosine of, and still 18t. So we're going to use H for high noon shadow. So our sunset shadow, we used S of t, and our high noon shadow, we used H of t. So these are our two shadows. These are the equations we're supposed to remember from our previous unit. And it's been a while. Hopefully you've got those. I should have given you a chance to think about them. If we'd been in class, I would have, but there we are. Now here's the tricky part. Based on your previous work, you probably wrote these equations in terms of degrees, which we did, because we took 360 and we divided it by 20 to get 18t. We want to change it to radians. So what change is going to happen? So looking back at the sunset shadow, the 30, the distance above the ground, has nothing to do with the angle. The 20, the radius, has nothing to do with the angle. The thing that has to do with the angle is this 18. So that is what is changing. And the same in this one. This is what is changing. So we're just going to go in radian mode. So what do I do? Well, 360 degrees is 2 pi radians. So that's exactly the same measurement. So we're going to do the same thing. 2 pi is now going to get divided by 20 seconds, leaving me with pi over 10. So this is radians. So my sunset shadow, S of t, in radian mode is 30 plus 25 times the sine of pi over 10 t. So that's the hard one. I would like you to try to do this high noon shadow in terms of radians. Go ahead and pause the video. Look back at what you wrote for number 2 and see what needs to change. And so pause your video. Are you paused? Have you paused it? Okay, pause the video. And so I get H of t equals 25 times the sine of pi over 10t. So the only thing that changes in our two equations is what we call the argument, which is now in radians. Where in questions 1 and 2, we were in degrees, and we were very naturally in degrees. I didn't even stop to think about being in anything but degrees. 360 divided by 20, and we got this the same way. So this puts me in radian mode, which is so much easier. Can't stress this enough. We're going to be in radian mode from this point forward. Now, in the equations we wrote for question number 3, where on the Ferris wheel was the rider located at t equals 0? This is the initial position. So if we think about this, we've got our Ferris wheel. We know it very well. We're always starting here. That's the initial position. So this is t equals 0. Where is the rider? So think about it again in these two equations from 3. So when t is 0, wait, excuse me, I have the second equation wrong. I wrote sine. Cosine, excuse me. So cosine and sine. Okay. And so, where is he? So go ahead and pause and think about that, and I'll be right back with the answer. So I went ahead and did these the trigonometric way instead of the thinking way. I knew the answers, but trigonometry is so much more fun. So I just went ahead and plugged in 0 for t, and pi tenths times 0 is 0, and the sine of 0 is 0, and so I got 30 feet, and cosine of pi tenths times 0, so the cosine of 0, the cosine of 0 is 1, and so I got 25 times 1, or 25 feet. So those are pretty straightforward, kind of crunch and grind. You could do it that way, or you can do it, and I think about this, the shadow on the wall is the radius plus the position off, so 30 and 25. And so I got the wrong answer. What's going on? How did I get the wrong answer? Sine is... Okay, hang on. I forgot what I'm talking about here. So this is 30. And so that's why it didn't make any sense to me. The part above the ground right here is 5 feet. And so that's where my 30 comes in. So we know that same kind of thinking thing. So then for the cosine down here, we're looking for how far away he is from the center, which is 25. And so those are going to be our two answers. And that's that. Okay, so next problem and last problem we're going to do today. We're going to save the rest for tomorrow. Revise your equations from question 3 so that t equals 0 is instead of at this our initial position here, which is where it's been the whole time, instead of being here, we're going to move our initial position there. So instead of being here, this is going to be t0. Because not everybody starts in this gondola, so we're going to put somebody in this one. Let's see what we can come up with. So stop, think about it, and see what happens. If you haven't already, pause the video. Okay, so for our sunset shadow, I've stuck with sine here. You can change that if you want, but it's a little trickier. I still want to be talking about the vertical distance off the ground. And so I need times 0 to give me 55, because I know that's the right answer. So I know when I plug in 0 for t, I'm supposed to get 55. So this is all I've done right now. And I also know that my shift on the circle from here to here is pi over 2, because that's the shift of the circle in radians. So what should I do? And I'm going to leave this kind of as a mystery for you right now. I don't want to give away the answer. We'll talk about it tomorrow in class. But it has something to do with pi halves for both of these. And I've put it in parentheses and I can't quite remember, and I'll have to double check it. I think pi halves goes in there and changes and does crazy stuff, and we'll get into it later. But the shift on the circle of the movement of its position is the key here. We haven't done this. We've shifted it up, we've shifted it down, we've shrunk the wheel, we've sped up the wheel, we've made it go faster, we've played with several different things, but we haven't played with this, which is called a phase shift, which is a shift left and right. So I'm going to leave you thinking about this, challenge you to figure out where that pi halves goes in this equation. Good luck, and we'll talk tomorrow.